Yes. Today we are going to discuss a very important topic called Reynolds two-dimensional equation for hydrodynamic bearing. Reynolds two-dimensional equation for hydrodynamic bearing. So in the previous class we discussed about important assumptions were made for this derivation. We already discussed. So based on the assumptions, we are going to derive. So here first we consider the converging oil film. This is what the a converging oil film. Okay, a surface B is fixed. This surface which is hatched, it is a fixed or a stationary surface. Okay, so it is a stationary surface and the surface is stationary or fixed surface, and the above yellow color, it is an another surface. It is called A, means it's a moving surface. It's a moving surface, and this one is called as a fixed or stationary surface. The surface A is moving with a constant velocity u, a constant velocity u, a moving plate or moving surface, it is moving at a velocity of u. Okay, in the direction x, it is in the direction of x. This surface is loaded with a vertical load. Here the surface is loaded by a vertical load, a w. This is called as a load. Okay, it is vertical load w in coordinate system as shown in the diagram. Here it is in the x direction, y direction, as well as in the z direction. This is a coordinate system. A surface A and B are assumed to be a large in the direction of z. When compared to z direction, this surface is very large, a perpendicular to the motion, so that a flow in this direction is neglected. So when compared to these surfaces and this direction, z direction, there is no flow in the z direction, means there is no end leakage. This derivation is belongs to the no end leakage. Clear? So there is no flow in the z direction, only the flow in either x or y direction. Okay, so because the surfaces are very too large when compared to this direction, so it is no end leakage. Okay, so now consider a small element, imaginary element. Consider a small imaginary element in the fluid film, which is between the surface shown in the figure, moving surface, and the stationary surface. The positive direction of velocity of the components are u, here it's a u, v, w in x, y and z direction. These are the velocities in x and y, z direction. Okay, here the h is the what the height of this, means it is a width of the fluid film, where the imaginary element, where h1 is the entry thickness and h2 is the exit thickness of the fluid film. When compared to h2, h1 is higher because it is in the taper. Okay, taper cross section. So because no flow in the z direction, the pressure along z direction is constant. Okay, the pressure along the z direction is constant, only the pressure changes in the x direction. And the pressure force acting on the surface of the element perpendicular to the x axis are in the equilibrium, and hence are not considered for the analysis. This is already we made in the assumption. The pressure across clearance is also constant. So pressure across the clearance is also constant because there is a perfect adhesion, as well as there is no inertia force. So that we already made that assumption, there is no inertia force, so that there is no pressure across the clearance. is constant. Therefore, the pressure force acting on the top and bottom force on the element is also equilibrium. Yes, in the top and bottom face, whatever the top and bottom face of this imaginary element, okay, pressure is constant. Whatever the pressure in the top, it's the same in the bottom. Okay, but the pressure in the right and left is different. Okay, so it causes the flow from left to right. So this is the left side and this is the right side. The flow is from left to right because the pressure more in the left side, less in the right side. But pressure in the top and bottom is constant. Okay. So here we enlarge this imaginary element here. So here in the x direction, y direction and z direction. Okay. And these are the velocities in the x direction u, y direction v and z direction w. And these are the forces which acting on imaginary element. Only four forces are acting on the imaginary element. So one force on the left side and on the right side and on the top and on the bottom. So this is a shear force, purely a shear force. Okay, and these are the pressure acting on the left side and right side face of the element. Here element is having a 6 faces, top, bottom. Okay, and there is no force in the z direction. So z direction there is no force, we neglected, so that there is no forces in the z direction. Only 4 forces we consider for the equation. So at the equilibrium we consider for equilibrium, the element is in the equilibrium. So we first note on the forces. The pressure force acting on the left and fourth face of the element. So left hand face, what are the pressure force? Here the pressure force. So P is the pressure, okay, and this is what the area. So pressure into area, it gives the force. So here the pressure which is acting on the area. This is what the area, okay. So on this area, this pressure is acting. That's why it is a pressure into area which gives the force here, okay. So P into gy dx. Similarly, the pressure force acting on the right, which gives the, yes, P plus dP by dx into dx, that pressure into area dy dz. Okay, this is the equation 2. We can call it as equation 1 and equation 2. Similarly, another two forces which are acting on the same imaginary element, that is what shear force on the top surface, shear force on the top surface and shear force on the bottom surface. So shear force on the top surface is tau x. Okay, it's the tau x is the shear stress. It is called a shear stress into area which gives the force. So tau x into area dx dz. So this shear stress is acting on this area, that is what, on the element. And here also same thing, area is same. Okay, this is the area, but the only thing is shear stress is changes. Okay, tau x plus d tau x by dy into dy. Okay, here this is a tau x dx into dz, but here there is a change in the shear stress. It is not same on the top and bottom. So here some more dx, but here dx plus d gx by dy into dy, because it is in the changes along the dy direction, that's why written dy. Here changes in the x direction, that's why written dx. Okay, so this equation we are going to consider. There are 4 equations. One is on the left hand face, right hand face, on the top and bottom. There are 4 equations or 4 forces we got on the imaginary element, and at according to the assumptions, we already made us several assumptions. In that, some of the assumptions state that there is no inertia force. So no inertia force means there is no force due to their own mass. Okay, that we are going to neglect it. Means there is no end leakage. Then the only 4 forces are the equilibrium. Then the equation will become, we equating all these into a one equation. Clear? A one equation, that is first we write according to their directions. If it is in the moving towards the right, it is called as positive. It is moving towards left, it is called as negative. Okay, so based on that we are going to equate. The first is the right hand side, then left hand pressure. Here the shear stress on the top and this is on the bottom is equal to 0. Equilibrium means it is in the equilibrium state. So if we expand this, if we expand this and this, okay, we can write like this. So P dy dx minus, okay, P dx dy minus dp by dx dy dz, okay. If we expand this, we will get these two, and if we expand this, we will get these two components. And if you simplify, we can clearly cancel these two terms. This is plus and minus, same terms, and this is a plus and minus, the same term. If we cancel these, we'll get a final equation, only remaining these two components, minus dp by dx dy dz minus d tau x by dy dx dy dz is equal to 0. If you take dx dy dz as a constant fact, common term here, okay, then it is become a negative as also common term. So minus dp by dx plus d tau x by tau y. So if you multiply this into the right hand side, it is become 0. Okay. If you move to the right side, so 0, anything by 0 is 0. So finally we got the equation 5. This is a equation 5. Okay, this equation 5 is equal to dp by dx is equal to minus d tau x by dy. Just expand and send one term to the right side. This term to the right side. Okay, so here minus and dp by dx minus, this is minus, and if you send one term to the this side, so it is become plus and here minus. Okay, minus plus dp by dx is equal to minus d tau x by tau y. This is the term what we got. This we call it as a equation 5. Next, and we also made one more assumption. The fluid is Newtonian fluid, means the fluid, whatever the fluid we are using, it follows the Newton's law of viscosity. It follows the Newton's law of viscosity. So then the fluid is called as Newtonian fluid. So according to that, this is what the equation. We already know that the Newton's equation is equal to tau x is equal to a minus mu du by dy. Okay, du by dy. This is the velocity. This is the thickness of the fluid film. It changes with respect to the changes. This is what we already discussed in the Newton's law of viscosity. Okay, so here minus means the velocity goes on decreases with increase in the thickness. Because there are two surfaces. One is a stationary surface, and here in the stationary surface velocity is 0, and here it is a moving surface, so velocity is maximum. When the thickness increases, velocity increases. When thickness decreases, velocity decreases. So this is what indicated by negative sign. Okay, so substituting this equation 6 in the equation 5, substituting equation the equation 5, finally we got dp by dx is equal to minus. Already there is a minus, that minus and this minus get cancelled. So finally mu d by dy du by dy. So that we can call it as a dp by dx is equal to plus mu that two terms d into d, that is tau. Means it's a very small quantity. Tau means it's a very small quantity. Tau square u by tau square y whole square. Okay, and if you just move this mu into left side, then tau square u by tau y whole square is equal to 1 by mu dp by dx. We can call it as this is the equation 7. Next, integrate equation 7 integrate equation 7 twice with respect to the y. So y is a varying component in our equation. It is changes. Y is changes from 0 to maximum. That's why we consider y. So d, one side is a u varying component, velocity is a varying, and in the another side the thickness or whatever the width or the fluid film thickness, that is y, it changes because it is a taper surface. So it is changes, keep on changes. When the imaginary element changes along the length of the surface, the y is also changes. Okay, it changes from h1 to h2. So here we consider one side is a u and another side is a y because for the integration purpose. Okay. So in the first what we made is, so we written just as it is the equation and integration. Here there is an integration and here integration. These are the constant terms. Okay, 1 by mu dp by dx is the constant. But only u and y is changing. So integration of dy and integration of one term, that is what, dou square. So here it is also dou actually. Okay. So if you integrate, we get this equation. Dou u by dou y 1 by mu dp by dx y, and c1. C1 is the integration constant. It's a constant because there is no limits. That's why we got the constant value. And second, if you integrate again this term and moving this into the right side, okay, this is what the equation integration. Here dy and c1 into dy. If you integrate, if you apply integration, it is become u is equal to 1 by mu dp by dx. So y, already there is a y. So y dy integration. So y dy integration is equal to y square by 2. Okay, so y square by 2 and c1 dy. Okay, c1 integration of dy is equal to y, c1 y, and plus c2, it is an constant, integration constant. Just a minute. So it is called as a integration constant. And we have to find out the values of c1 and c2 because we have to find out the integration constant value by using boundary conditions or limits. By using limits or boundary conditions, we have to find out the values of c1 and c2. And once we got the values of c1 and c2 and substitute the above equation, we get the final velocity equation for Reynolds equation in 2 dimension. Okay. First, when u is equal to u means maximum. Yeah, when velocity is maximum, the velocity is maximum when u is equal to 0. This is a surface, two surfaces. Okay, this is a fixed surface and this is a moving surface. So here velocity is maximum and y is equal to 0, and here velocity is 0 when y is equal to either h. Okay, so when the h means this surface, when it is equal to this surface, the velocity is minimum, and here velocity is maximum when u is equal to u maximum. U is equal to maximum when y is equal to 0. Y is 0 on this surface because there is a perfect adhesion. We already made this assumption. There is a perfect adhesion. So whatever the velocity of this plate is, the same top layer of the fluid film is also having the same velocity. And here whatever the velocity of this surface is also same having the, because there is a perfect adhesion between the fluid film as well as the surfaces. That's why the same velocity. Here is velocity is 0, here velocity is maximum u. Okay, these two limits, limit 1 and limit 2, by using these limits we have to find out the constants c1 and c2. Okay, so by substituting this, as u is equal to u, okay, and y is equal to 0. Here if you substitute y is equal to 0, this term is become 0 and this term is also become 0. Only we got c2. So c2 is equal to u. c2 is equal to u max of u. Simply we call it as a u. Okay, by substituting limits. Similarly, in the second, by applying another limits, by applying the other limits when velocity at the fixed surface, here velocity is 0, where y is equal to h, because imaginary element it is in the h. Okay, here 0, so y is 0, y is h. So velocity minimum and velocity maximum, so these limits we are using here. Okay, and if you substitute that 0, 1 by mu dp by dx h square by 2 plus c1 into h, and this is already we got c2 is equal to u. So substitute that, okay, u, it is u, capital U. And if you simplify this, we got this equation by simplifying. And finally, we want C1 value. So C1 is equal to minus 1 by 2 mu dp by dx h minus u by h. Okay, so we got the values of C1 and we got the values of C2. We got the both values, integration constant C1 and C2, and substituting these C1 and C2 in the main equation u, and finally u will become u is equal to 1 by mu dp by dx y square by 2 plus that is for the C1 value minus 1 by mu dp by dx h by 2 u, capital U by h into y, plus C2 means capital U. Okay, and rearrange the term. This is what the rearranging the term. If you rearrange and simplify, okay, I'm just rearrange and simplify. We got the final equation. So u is equal to, this is what u is equal to 1 by 2 mu dp by dx is a constant, we take out this constant, y square minus h by u. We already taken this constant u 2 as a constant, mu is a constant, 1 by 2 mu dp by dx, so remaining is y square minus h y. Okay, and here if you arrange these two, okay, I made separate similar terms. Okay, capital U by h y plus u. Here if you take u as a constant, finally h, okay, minus y, because here minus, here h, okay, and divided by h. If you simplify h get cancelled, only u is remaining, and minus u h by y is remaining. I just simplify this term into by taking out u as a constant, as well as I made it positive, and here minus y, because here minus term is there, here plus term is there, so I take first plus term and minus y by h. Okay, this is we call it as a equation 11. This is a velocity equation for Reynolds two-dimensional equation in hydrodynamic bearing without end leakage. There is no end leakage. If you consider end leakage, the equation will changes. Here we only, there is no end leakage, means z direction is 0, we are neglecting. That is equation 11. So this is what the pressure and velocity distribution according to the equation. According to that equation, okay, means the so previous equation, here we made, this is a pressure distribution. Pressure is maximum at the center and minimum at the entry and exit. Okay, exit and entry pressure is minimum. Here pressure minimum, and here pressure is minimum because it is in contact with the atmosphere. Here pressure is maximum, so we got the maximum pressure. Okay, this is what maximum. Here pressure is minimum or atmospheric we can call it as atmospheric pressure. And this is what the pressure distribution, gradually pressure increasing up to maximum and gradually pressure decreasing to the minimum. And this is what the velocity distribution, velocity. Okay, so here velocity u at this a cross section, the a cross section, the velocity is here, it is u is equal to minus u1 and u2. Here velocity is u, okay, u2, and here velocity is u1 plus u2. Means velocity, the previous equation what we got is it's having a two set of velocity. One is velocity is because of the moving plate, okay, it is because of the moving plate, and another one velocity is because of the change in the pressure. The pressure will causes the velocity. Somewhat pressure will contributing to the velocity. There are two terms, so that is we u1 u2, that we what we call it as u velocity. There are two terms contributing. First u1 means that is an 1 by 2 mu dt by dx y square minus hy. This is one term, plus another term is u h minus y by h. This is what the velocity, correct? We got the equation. Here we can call it as a, this is a u1 and u2. There are two velocity. One is just because of the moving plate, and other one is because of that change in the pressure, it causes some velocity. That velocity we can consider as a u1, and velocity by the plate we can call it as a u2. Okay, so in the first cross section, here in the first cross section, you can observe that here the velocity, only this is a velocity, only this is what the velocity, the line, whatever the line, parallel line, it is a velocity maximum to the minimum. And here dash line and this curve, there is a negative velocity, means here there is a negative velocity. And here dash line, and it exceeds the dash line, so that here there is a positive velocity. That's why velocity u is equal to u1 plus u2 I return. Means here in this cross section, the velocity is, one is because of the plate and because of the pressure, okay, plate and pressure here. But here only the velocity is plate, only the velocity is plate velocity, and that minus pressure, means the pressure velocity is negative. Here the pressure velocity is negative, that's why this is a gap, and here there is a excess, it is a plus, okay, plus plate velocity and velocity because of the pressure. Here plate velocity minus the pressure, means this pressure creates the minus velocity. Because of moving this, there is a taper in the surface, the fluid will force moving from left to right, okay, because of reducing the cross section, converging, we already said that it is a converging. So because of converging, the area goes on decreasing. If the area goes on decreasing, means there is an increase in the velocity, correct, because there is a cross section reduces, so velocity, the same amount of fluid is flowing, so but less amount of area, so it increases the velocity, and some amount of the fluid will flow back, flowing back, means it will create the negative velocity at the entry. And at the exactly middle, so the velocity is equal to only plate velocity. Whatever the plate velocity, it is exactly, that's why it is maximum, okay, pressure is maximum here, because velocity is u is equal to only u2, but here there is a negative velocity, and here it is a positive velocity, okay, it is in the exit, and here it is in the entry. Clear? Here in the middle it is a maximum, that is what I return. This is a negative, okay, and this is what the positive. So u is equal to u1 plus u2 I return, and u is equal to u2, total u2 minus of u1, minus of u1, that gives the u, and here it is same, u is equal to u. So pressure is maximum. This is what the, this is how the pressure and velocity distribution in the hydrodynamic bearing. Clear? So next we need a flow rate. Already we got the velocity of u. So for flow, we have to consider again imaginary element, the same imaginary element. It is in the cubic. Consider a discharge through the element. Means that cubic element, how much the fluid is flowing through. Discharge we have to consider. Okay. For the discharge, we know that discharge or flow rate is equal to velocity into area. So because the fluid as assumed is a incompressible, we already made in the assumption it's incompressible. The volume quantity of lubricants are flowing to the element which is shown in the figure is equal to the quantity of the lubricant oil flowing out of the element. Whatever the oil enter to the element is same, the oil exit to the element. Entry is equal to exit. Whatever the quantity of oil enter, which is equal to whatever the quantity of oil discharge. Entry equal to discharge because of it is incompressible. Okay. So these are the x, y and z direction. Here dx, dy, dz are the thickness of the element in the z direction, the x direction and in the y direction. And these are the quantity of fluid flowing in this phase. There are 6 phases. This element is having a 6 phase. One cubic element is having a 6 phase. So this phase is called as 1 and this phase is called as a 2 and this phase is called as a 3 and this bottom phase is called as a 4 and this front phase is called as a 5 and this back phase is called as a 6. Total 6 phases. And the phase 1 and phase 2 interrelated in the x direction and phase 4 and 3 interrelated with the y direction and 6 and 5 interrelated with the z direction. Okay. So here this is the component, the velocity into area which gives the flow, whatever the flow in which is equal to velocity into area flow out. Okay, flow in, flow out. The velocity here u, but here it is not u because of this change in the dx direction. So u plus dou u by dou x into dou x. Okay, here same thing in the y direction. Here v, here u is the velocity in x direction, v in the y direction, z in the z, that is what, z direction, u v w. Okay. So v velocity and w is a velocity. There in the z direction, in the y direction, and here in the x. This is what the element we consider. Okay. At equilibrium, okay, whatever the force, the right side is equal to left side. Whatever the force, uh, in the top force is equal to bottom force. So all the forces which is in the at equilibrium, so it is at equilibrium. Okay, we can write this equation like this. So u gy dx, v gy dx, and w dy dx. Okay, these are the positives, and this is what opposite direction. That's why it is equal. Either we can equate it to the 0 by considering positive and negative, or we can move this negative to the this side, it is become positive. Okay, that's why I written like this. This is one term, two term, three term. And if we expand this, this is what the equation we got. This equation we can cancel by expanding. Okay, because here positive, here positive, so we can it is left side and right side we can cancel, and this we can cancel, and w we can cancel. And at the same time, okay, here it is become a 0, and here only dou u by dou x dx means that is dx dy dz, dx dy dz, dx dy dz. So it is equal to dy dx dz. If you move or multiply left side, it is also become 0. So 0 by anything is 0. Okay. So finally we got this equation. So 0 is equal to the only term dou u by dou x plus dou v by dy and dou w by z. Okay. And here this is, we can call it as a 0 because no flow in z direction. Okay, we already made in the assumption, so that it is become 0. So finally dou u by dou x plus dou v by dou y is equal to 0. And if you move this, dou v by dou y is equal to minus dou u by dou x. We can write this, just moving this to the right side, so it is become minus. Okay, and introducing the value u from the equation, we already got the equation, the velocity equation we already got from previous equation. Okay, substitute, this is what the u, and here since velocity, the velocity v is equal to 0 at y, or y is equal to h, this is we already know the limits, this is already we know the limits, because it is a taper surface, the velocity here maximum and velocity here minimum, here 0, here it is u. Okay, that we can use. So integrate, because we want to integrate the equation, so that if we integrate, you apply this one side dy du dv, and another side the equation. So integration, this is 0 to y, so integration of v with respect to 0 and h, it is become 0. Okay, so 0 is equal to, one side is become 0 because it is the integration, apply integration. But here in the right side, du by dx, that dy here I multiplied right side. Okay, only dy is remaining, so 0 to h. If we take minus as a constant and substitute the value of u dy, here y and y, so we can easily integrate for integration. Since the limit h is a function of x, is a direction of x, here there is no x term, so that we cannot apply integration, we cannot do the integration for above equation. Okay, here the limit is 0 to h, it is in the x direction. Okay, x direction, but here we got the dy in the y direction, so we cannot apply the integration for this. If condition like this, we have to use a integration method by following this. It's one of the important either integration solved by parts method like this. Here it's a one tau and rho equations. Okay, it's a tau and rho equations. This equation you get it in the data handbook. Okay, so in the data handbook this equation is there from data handbook. By using this equation, we simplify this unintegrable equation to integrating equation. This equation we cannot integrate. Okay, by using this equation, by comparing and simplifying, and if you substitute in this equation, it convert to integratable form. It is presently it is not integratable. Okay, if you want to integrate this equation, we have to compare as well as simplify, we get the equation, that equation we can easily integrate. For that we have to use this equation. Okay, here there are so many terms, it's a left side and right side, we just compare left side as well as right side. Here first this rho x is equal to 0, rho x means 0, so 0 is there, here rho x is there, so rho x means 0. Tau, this is what we can call it as a tau. Okay, so tau x, here tau x means h, so tau x is equal to h. Okay, this is one by comparing like this, and here f x comma y, here f x means this whole term, that is what u. So I just compare, here u is there, the same thing here, and dy, of course there is a dy. Okay, next here some more terms are there, this is dy. Okay, I return, if you expand this, we got this equation. Here tau x, rho x is there, okay, no fine, and here u is there, dy is there, fine, but tau dash and tau dash is there, that we have to find out. So if you differentiate this tau x, if you differentiate, we get this. If you differentiate, we get this tau dash and tau dash. So if you differentiate this, again we get the same thing. If you differentiate this, gy by dx, that is what term we get. Clear? And similarly, this is f of term is there x, tau means h, and this is f of x, tau means 0. Okay. So here it is multiply tau dash, that is what we got the equation. Here if you multiply this, it is entire terms become 0. Okay. Yes. Here you clearly get, after substituting these equation in the right hand side, okay, these are the another terms. If you substituting in the equation, substituting in the previous equation, 0, already we got the 0, and here d by dx, integration 0 to h, u, okay, this is a term, u into dy, minus, if you, this is a 0, 0 into anything, 0, and this is a term 0, and 0 into 0, 0. Okay, finally d by dx, integration 0 to h, u by gy. So this equation we can easily integrate. Okay. The previous equation, what the equation 15 is not integratable. That equation 15 to integratable equation by using u equation, and by 0 to h we can easily integrate. The integration is now possible, and apply integration. Okay. So apply integration here. This is what the integration means, u equation. This is the equation u. Okay. And now after substituting, this is the equation, apply integration and simplify. If you apply integration and simplify, finally you will get this. Okay. Apply integration as well as limits. By applying integration and limits, finally you got this equation. And if you simplify that equation, by rearranging 0 this side, first you expand, I expanded terms, 2 terms, this into 2 terms, okay, and if you move left side, it is become d by dx, dp by dx, h cube by 6 mu is equal to u dh by dx, okay, and finally move this term into this side, so d by dx into h cube by dp by dx is equal to 6 mu u dh by dx. This is what the final Reynolds equation. This is called a final Reynolds equation for two-dimensional with a no and leakage in two-dimensional. Okay, this is a equation 17. Equation is called Reynolds equation for 2D. Integration, applying limit, and rearranging, we got this equation. Okay, this is how we have to derive the integration. With the help of integration and differentiation, we have to derive the Reynolds two-dimensional equation. Okay, and here I clearly derive Reynolds equation here. Just use my notes. Okay, Reynolds two-dimensional equation. This is what the figure. You have to write down and you have to explain the theory part and consider the equations at right face, left face, shear stress top and bottom, then equating equilibrium, and finally got this equation. Once you got, use the Newton's law of viscosity. Then by substituting this equation in the above equation, we got u value, and by double integration with respect to the y, finally we got the u in terms of C1 and C2 integration constant. These constants by removing by using limits u is equal to capital U, y is equal to 0, and u is equal to 0, y is equal to h. Finally C1, C2 value we got, and substituting, finally we got the final velocity equation. There are two terms, this is a u1 and u2. It is because of the plate, and this is because of the change in the pressure. dp by dt means pressure. Change in the pressure, there is a velocity u2, u1 and u2. This is a plate and taper surface, how the velocity and pressure changes I explained, and this is what are cross sections. And finally, for discharge, whatever the amount of enter is equal to discharge, that is what velocity into area, we got the discharge. And we consider all the elements u, v, w in x and y direction velocities, z direction we neglected, and finally got this. And substituting this and apply integration, but integration is not possible, it is a not integratable form. So this equation we convert or simplify using this. This is what we got from the data handbook. Here compare and simplify, we got the integratable form, and this equation 16 is a integratable, and apply integration and rearrange and refine. Finally you got Reynolds two-dimensional equation. Equation 17 is called Reynolds two-dimensional equation. So this equation may ask for whole 20 marks, okay, in your examination. It's a most probable question.